Welcome to part two of our look at V12, the buffers lab. This video is going to walk through the actual procedure in terms of what you're going to do and what you're going to need to make in the virtual lab space. And then we'll get into the calculations that you have to do as part of the post-lab analysis. So let's start by going and looking at the procedure itself. So you're familiar with this already, or at least you should be. We are going to be going to the Chem Collective's virtual lab. So do a control click here in the procedure to open up this in a new window. And it might be worth your while here to actually set up a split screen of sorts so that you can do what it is that you need to do. So you are going to create a pair of buffers. So part one here, you are going to create a buffer with acetate and acetic acid and one of ammonium chloride and ammonia. The process by which you do this is not terribly difficult. You're going to need the distilled water. You are also going to need some glassware. So in particular, you're going to need a couple of 100 milliliter volumetric flasks. And you're going to need some solutions. So let's start with the acetate buffer. You're going to need the weak acid, acetic acid, 1 molar. And you are going to need the conjugate base, sodium acetate, also in 1 molar. So taking one of these volumetric flasks, I'm going to right click and rename it. This is going to be my acetate buffer. And in that, I am going to put 30 milliliters of the acetic acid and 30 milliliters of the sodium acetate. All right, I'm done with these. I'm going to add 40 milliliters of water to get me up to the 100 for the volumetric flask. So there's my acetate buffer completely made and ready to go. For my ammonia buffer, I'm going to need from the stockroom the weak base, ammonia, again in 1 molar quantity. And I'm going to need the conjugate acid, ammonium chloride, also in the 1 molar quantity. And according to the directions, I need 40 milliliters of each of these. So 40 milliliters of the acetate, or I'm sorry, the ammonium, 40 milliliters of the ammonia, 20 milliliters of the water. Now I've got my 2 buffer solutions. Before I start putting all of this stuff away and moving it off of the bench, my data table here, I need to record pH values for each of these solutions in their initial concentrations. And remember to do that, you just click on each one of them and it'll give you the pH values that you need. Once you have those, then you can remove these from the workbench just by right-clicking on each of them and clicking remove. All right. So that's part one of this procedure, is just making the solutions themselves. The second part of this procedure is I'm going to take these and move them into some beakers. So in total, I'm going to need 4 beakers. This one is going to be for the acetate buffer. This one is going to be for the ammonium buffer. This one is going to be for water. I'm going to put an acid designation next to that because that is going to be the one that I add acid to. And this is going to be the one for water that I'm going to add base to. Now, to each of these, I'm going to add 50 milliliters. So I'm going to add 50 milliliters of my buffer to my beaker. I'm going to add 50 milliliters of my ammonium buffer to that ammonium buffer beaker. And I'm going to add 50 milliliters of water to each of my water beakers. So now I've got each of these right here. And I can see that the water is at pH of 7. The ammonium buffer and the acetate buffer are at their respective pHs as well. The next part of this procedure 1 is to run through each of these scenarios and add small amounts of acid and base to each of them. And so we're actually going to need 2 more beakers for this. So we will need a total of 6 beakers. So we're going to end up removing that volumetric. That wasn't my intent, but so in total, we will end up having 6 of these solutions. We will have water that we add acid to. So I'm going to put all of these here. I'm just going to put them in order kind of the same way that they appear on the screen. We're going to have water that we're going to treat with acid, acid that we're going to treat with acid, base buffer that we're going to treat with acid, water that we're going to treat with base, acid buffer that we're going to treat with base, and base buffer that we're going to treat with base. And to these, we're going to add strong acids, 3 molar hydrochloric, and strong base, 3 molar sodium hydroxide. And so we're just going to follow the process here as we go. So initial pHs, again, all we need to do is click on each solution. It'll tell us the initial pH of those. So that goes in this top line here. So I can put in as the original solution, the DI water had a pH of 7. The acidic buffer had a pH of 4.76. The base buffer had a pH of 9.25. And then I'm just going to follow the path here and add the small amounts. And as I add these small amounts, I'm going to monitor the pH. So I drag the acid over here. I add 0.1 After adding 0.1, I can see that my acid has gone from a pH of 7 to a pH of 2.22. The next step is half of a milliliter of acid. I've already got 0.1 in there, so I'm going to add 0.4 more. I can see now that the pH has dropped to 1.53. And I do the same thing all the way through. When I go to do the base, I'm going to take the sodium hydroxide, drag it over to the base solution, and do the same thing. 0.1 in. And we can see that the pH jumped to 11.77. And then I'm just going to keep going. 0.4 more. $12.47. And so on and so forth down the line. So that's how I collect my data for data table 1 and data table 2. For the next procedure, making a buffer with a given pH, you are going to have to make 100 milliliters of a buffer with a pH of 4.75. You are going to go through the calculations like you did in the pre-lab to determine what species you want to use and those kinds of things. You're going to measure the pH, calculate the percent error. So there are lots and lots, if we clear the workbench here, there are lots of possibilities, lots of choices. The thing to kind of keep in mind is that with a pH of 4.75, we want to look for acids with pKa's in the 3.75 to 5.75 range. That's really the only way that we're going to get to make this buffer work the way that it does. Now, in truth, we want that to be as close to 4.75 as possible. The closer it is to 4.75, the easier it will be to make that buffer. And keep in mind, we are also going to only make 100 milliliters of that buffer. So if you do the calculations correctly with the Henderson-Hasselbalch equation, should be pretty easy to do and set up the ratios exactly the way that they're supposed to be. But that is what you'll have to do for that procedure. Again, not too terribly difficult, but it is something that you might have to do a little bit of trial and error with, especially if you make any kind of minor calculation mistakes. And all of that is addressed here in analysis question number 7. So that's how you do this particular lab in terms of the procedures here in lab archives and on the virtual lab space. What we're going to move into now is looking really at those post-lab questions and at the data and results questions here, where you got to do some pretty significant calculations to figure out what's going on inside of that reaction and what the theoretical pHs should be. And so for that, I'm going to give you a little bit more context. The context I'm going to give you here comes in the form of, again, a little presentation just to go over this other part of buffers and buffer calculations. So we know that buffers work by having that weak acid conjugate base pair present, and that the success of buffers in resisting pH lies in that inner conversion between the conjugate acid and the conjugate base and each other. That's how buffers ultimately work. And so when we see a strong acid added to the system, we know that the strong acid reacts with the conjugate to make the weak acid, the conjugate acid. And the net result is that we see an increase in the reaction. We see an increase in the reaction, in this case for the carbonic acid, a decrease in the bicarbonate reaction that generally leads to a shift to the right, which would increase the concentration of hydronium slightly and make the pH go down. And when bases do this, again, we see that the base reacts with the conjugate acid to give us the conjugate base. The conjugate acid concentration is going to go down. Conjugate base concentration is going to go up. We see this as a net effect on a shift toward the reactants, a shift to the left, which means that the hydronium concentration is going down and the pH is going to go up as a result. Now, this is a concept that we haven't talked a whole lot about because we've been in equilibrium so long. It almost kind of makes us forget that some reactions do actually go to completion and have 100% or near 100% conversion. And because of the nature of the acid, the fact that it is a strong acid or a strong base that is doing these reactions, we assume exactly just that. They are going to go to 100% completion. They are not going to go into some form of equilibrium. And so these reactions between the conjugates and the known characters are completely one-sided. Which means we're going to do something a little bit different to monitor their progress. We've done ice tables throughout equilibrium, and those ice tables have been used to monitor changes in the equilibrium as we go from one equilibrium state to another. or as more importantly, more concisely, as we go from the initial set of conditions to the equilibrium set of conditions. Well, now that we are throwing in these acid and base kinds of considerations, we understand that the adding of the acid and the base are going to upset the equilibrium and cause the equilibrium to shift. And so we're going to need a different kind of an ice table in order to monitor these changes. The ice table that we're going to be talking about here is a modified ice table. And that modified ice table is going to allow us to look at, okay, here's how much of each reaction that I started with. I'm going to start with some amount of hydrogen, some amount of weak acid. I'm going to add to it some amount of hydroxide. I also had some amount of the conjugate base there at one point in time. Well, I know this goes completely this way, so my rules of limiting reactants are going to tell me that I'm going to go until this reaction breaks, until it stops, which means this amount here of the hydroxide is eventually going to run out. And when it runs out, that's how much of the conjugate acid is left. And this is how much of the conjugate base is now present. And with these values, I end up having a mole ratio that I can use in the Henderson-Hasselbalch equation to figure out what the pH is. And so that's really what we're going to be doing in these calculations, is so long as we stay in this system where we still have a buffer, we are going to see buffer-like tendencies, which means we're going to be able to use the Henderson-Hasselbalch equation to calculate and estimate that pH. So long as we still have conjugate acid and conjugate base present after this hydroxide or after this hydrogen ion does its thing, we'll be able to use this modified ice table and the Henderson-Hasselbalch equation to predict the pH. Now, if we go outside of those boundaries, if instead of having half of a mole of hydroxide, we ended up having more than that, well, then that's going to cause our HA to run out, and we no longer have a buffer system. The buffer system is said to be broken, and we have to use other kinds of calculations to figure out what to do with it. So let's take a look at an example here. Here I've got a buffer being made of with 0.250 moles of nitrous acid and 0.550 moles of sodium nitrite in enough water to make 1 liter of solution. First question is to determine the pH of the buffer. Second question is to determine if what the pH will be after we add 5 milliliters of 2 molar NaOH to this buffer. Now, for the first part, we're going to use the Henderson-Hasselbalch equation. Remember, the Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the concentration of base over the concentration of acid. Now, one of the nice things about the Henderson-Hasselbalch equation is since it's all one solution, we don't actually really truly need concentration for B or A. We can make do with moles in both cases, because if I take the moles over liters in both circumstances, I can see that my liters are going to cancel because it's one common solution, and I'd have moles here anyway. So that's going to be helpful for us because that means that we can simplify things. Even though this is in 1 liter of solution and the moles and the molarities are the same, it does make things a little bit easier for us because it covers us for when we aren't in 1 liter of solution. And we'll talk a little bit about that particular aspect of it in just a minute. So for part 1, pKa is the negative log of 5.6 times 10 to the negative 4th. And we're going with the log of the base, which is the sodium nitrite. So that is 0.550 over the nitrous acid, which is 0.250. From this standpoint, I can look at, okay, log of 5.6 times 10 to the negative 4th gives me a pH, or excuse me, a pKa of 3.25. .55 divided by 0.25 is 2.2. The log of 2.2 is 0.34, which means that the pH of this particular buffer at this moment in time is 3.59. Okay, so we've determined the pH of the buffer at 3.59. Now the question is, what is the pH of the buffer after we add the 5 milliliters of the 2 molar sodium hydroxide? We're going to use the Henderson-Hasselbalch equation again here, but we're not ready for it yet. We need to cover that manipulation that just occurred. And so to do that, we're going to use a modified ice table. And the modified ice table that we are going to use is going to take care of this particular problem and give us a means for calculating the values that go back into the Henderson-Hasselbalch equation. So since we are dealing with a strong base, we are looking at the reaction of hydroxide ion with the conjugate acid, the nitrous acid, which is the HNO2. That reacts to form water and the nitrite ion, NO2 minus. And my ice table sets up this way. Now, we mentioned before the idea that we can use moles in the Henderson-Hasselbalch equation, and we certainly can. However, we find that moles can be a little bit difficult to use at times because, well, there aren't usually that many of them. So what we tend to use for this technique is something called the millimole. Now, millimole comes from the same metric derivation as milligram or milliliter. It is 1/1000th of a mole. But what it allows us to do is that instead of taking molarity times volume in liters to give us moles, it allows us to take molarity times volume in milliliters to give us millimoles. And where that's advantageous for us is, since most of these kinds of things are done in small quantities, it works out pretty well to do it this way and keep it in millimoles, and the numbers stay nice and big and round as opposed to little and tiny. And sometimes we need to debate whether we're going to go into scientific notation or not. So using that methodology, the millimoles for hydroxide would be 5 milliliters multiplied by 2 molar, which would be 10.0 millimoles of hydroxide. For the nitrous acid, we have 0.25 moles times a liter, which is 1,000 milliliters. So we have 250 millimoles of nitrous acid. We don't care about the water. And 0.550 times 1,000 would give me 550 millimoles of the nitrite ion. Using our limiting reactants, I've got 10 millimoles of hydroxide, 250 of nitrous acid, The 10 millimoles of hydroxide are going to go away. We're going to add 10 millimoles of base. So in the end, no hydroxides left over. There are 240 millimoles of nitrous acid there. There are 560 millimoles of nitrite ion there. For the Henderson-Hasselbalch equation, that's all that we care about. We don't need to convert these into volumes. If we did, we would have to account for the volume of this solution is now 1.005 liters instead of 1.000. So if we were calculating the individual new concentrations of each, we would have to do that. Since the Henderson-Hasselbalch equation basically cancels that value out anyway, we can go straight into the solving. pH is equal to pKa. So again, the negative log of 5.6 times 10 to the negative fourth. If you were smart, unlike me, and wrote down the pKa value from the previous calculation, you wouldn't have to do this again. But you would have to do this one, 560 over 240. So the log of 5.6 times 10 to the negative fourth is 3.25 still. 560 over 240 is 2.3. So remember that this ratio was 2.2. It's now 2.33. The log of that is 0.37. pH is equal to 3.25 plus 0.37. This is 3.62. So in a buffer solution this big, adding that small amount of sodium hydroxide, even though it was pretty concentrated, had virtually no effect on the pH. It went from 3.59 to 3.62, a very modest, moderate change, if any. Let's take a look at one more example. This example, we need to calculate the pH of a buffer made by combining 85 milliliters of 0.13 molar lactic acid with 95 milliliters of 0.15 molar sodium lactate. This one is particularly difficult because these two substances are going to dilute each other. The new volume is going to be 85 plus 95 for 180 milliliters. And so your options here are to do dilution equations for each one, or again, using the millimole method and the Henderson-Hasselbalch equation, we're going to go pH is equal to pKa plus the log of the base over the acid. For pKa, we need the value for lactic acid, which finding it in our appendix table, lactic acid is 1.38 times 10 to the negative fourth. So that's negative log of 1.38 times 10 to the negative fourth. And then for the ratio, the base is sodium lactate, 95 milliliters times 0.15 molar gives me 14.25 millimoles in my numerator. 85 milliliters times 0.13 molar gives me 11.05 in my denominator. The pKa, 1.38 times 10 to the negative fourth, gives me a pKa of 3.86. 14.25 divided by 11.05 gives me a ratio here of 1.29. The log of that gives me 0.11. So the pH of this particular buffer as it stands is at 3.97. So again, you could have done this either way. You could have either done mutual dilution, use the dilution equation, take each one of those individually, divide them by 180 milliliters to get the new concentration for each, and plug them into the Henderson-Hasselbalch equation, or using the millimole method, multiply the milliliters times the concentration for each component, and plug those directly into the Henderson-Hasselbalch equation because the volumes will end up canceling out. From this standpoint, however, I can solve 1 and 2. For my first ice table, I've got hydroxide ion reacting with the lactic acid. I'm just going to abbreviate HLAC for lactic acid to give me water and the lactate ion. Initially speaking, I have 10 milliliters times 1 molar for 10 millimoles. For the lactate, we already established I've got 11.05 millimoles of lactic acid. Don't care about the water. 14.25 millimoles of the lactate ion. My limiting reactant here is the hydroxide, so I'm going to subtract 10 from both of the reactants, add 10 to the product. There's going to be no hydroxide left. 1.05 millimoles of lactic acid left, 24.25 millimoles of the lactate ion now present. The Henderson-Hasselbalch equation now comes out. We've already established the pKa of lactic acid is 3.86. Now I just need to put in my new values. I now have 24.25 millimoles on top, 1.05 millimoles on the bottom, 24.25 divided by 1.05. My ratio up here is now 23.1. So we can see we've had a big increase swinging toward the basic side of the ledger, which leads to 3.86 plus 1.36. We get a pH for this particular new buffer at 5.22. So we see a big swing in pH, but again, it took a pretty large sum of hydroxide to get us to that point. And even at that, it wasn't enough to swing us all the way into the realm of basic. So 5.22 is our value for number 1 here, 5.22. Now let's go ahead and look at what happens with the acid. So as far as the modified ice table is concerned, it's going to be pretty similar looking, just kind of flipped around. Because ultimately, what you are going to end up doing is kind of the same thing, only in reverse. So here I'm going to have the H plus reacting with the lactate ion rather, to make the lactic acid. 3 times 3 is 9 millimoles of acid. We have from the previous two problems 14.25 millimoles of lactate, 11.05 millimoles of lactic acid. Limiting reactants here tell us that the hydrogen is going to run out first. So I'm going to lose 9 from each of the reactants. I'm going to gain 9 of the product. There's going to be no hydrogen ion left over. 5.25 millimoles of lactate ion left over. 20.05 millimoles of lactic acid now there. Now we plug in those new values into the Henderson-Hasselbalch equation. pKa is still 3.86. We now go to the logarithm 5.25 over 20.05. 5.25 divided by 20.05 gives a value for the fraction of 0.26. So we are seeing that the ratio has flipped from being base favored to acid favored. That's going to give us a negative value here, negative 0.58, which gives a pH value then of 3.29. Oh, excuse me, 3.28. So yes, we do see a decrease in the pH, but it's a relatively small decrease in pH. Went down by less than 0.7 pH units. So these are the kinds of calculations that you are ultimately going to be expected to do in that post lab. And if we look through to the questions here, you can see we've got your modified ICE tables already set up here in Lab Archives. All that you need to do is do those little calculations to figure out what happened, what's left over, and then use your Henderson-Hasselbalch equation to figure out what the theoretical pH should be. So, and you'll see in the post-lab questions, you'll see similar kinds of questions in here to what we were just talking about. Determine the pH of a buffer. What happens if that buffer gets hit with acid? What happens if that buffer gets hit with base? How does it react with each one of them? So if you have any questions about things, please feel free to reach out to me or talk to me in lab about this. More than happy to help you get through this and to help kind of figure your way out as you go into these. But until next time, I will see you in lab.